next we are going to study about the cells when they are connected in parallel. What will be the EMF value, equivalent EMF, and the internal resistance, that is the value of small r. For that, let us consider the two cells of EMFs E1 and E2, internal resistance R1 and R2. Okay, the potential difference across the first cell, that is potential difference across the first cell E1 having the electromotive force E1 is V is equal to E1 minus IR1. Same way, potential difference across the second cell is V is equal to E2 minus I2 R2. Okay. Therefore, we can write from the equation number 1, we can write I1 is equal to E1 minus V divided by R1. Same way, similarly, I2 is equal to E2 minus V divided by R2. From the values of potential differences, we have taken the values of I1 and I2. If this combination is replaced by the single cell called as equivalent cell of the EMF, E equivalent, and internal resistance, equivalent internal resistance REQ, then this becomes I is equal to E equivalent minus V divided by R equivalent. Okay, therefore we know that in this parallel combination always the current divides, means the current in this combination is taken as the sum of the two individual currents here, I1 plus I2. We are already having the values of I1 and I2 here, and I also we know here. Substitute all the three values in this equation number 1. It becomes I is E equivalent minus V divided by R equivalent is equal to value of I1 is E1 minus V divided by R1 plus E2 minus V divided by R2. Okay, we are here substituting the values of I1 and I2 from all these values here. Now we have to just rearrange the terms. How will you rearrange the terms? We can write this one as E equivalent divided by R equivalent minus V divided by R equivalent. Same way, E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. On rearranging the terms, we will get E equivalent divided by R equivalent minus V divided by R equivalent is equal to E1 by R1 minus V divided by R1 plus E2 divided by R2 minus V divided by R2, right? So arrange again in the rearranging, again we get E equivalent divided by R equivalent. It is equal to, take this to the other side and this to the right hand side. You will get E1 by R1 plus E2 divided by R2 minus this one V by R1 minus V divided by R2. Okay, or again we can write this one as E equivalent divided by R equivalent is equal to E1 by R1 plus E2 divided by R2 minus V into 1 by R1 minus 1 by R2. Okay, so this one is plus 1 by R2 plus 1 by R1 plus 1 by R2. Okay, and we know that in the parallel combination 1 by R equivalent is equal to 1 divided by R1 plus 1 by R2, and also E equivalent is equal to E1 by R1 plus E2 divided by substitute here. You will get E equivalent divided by R equivalent is equal to E1 by R1 plus E2 by R2 and so on up to plus En divided by Rn for n number of cells. Okay, or we can write for n number of cells the equivalent resistance also becomes 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on up to 1 divided by Rn. That is the equivalent resistance for n number of cells, and this is about the parallel combination of the cells. What is the expression for equivalent EMF and the equivalent internal resistance? This equation also will be asked for 3 marks. In this video you are going to study about the Kirchhoff's laws. These Kirchhoff's laws are used to analyze the complicated circuits. There are 2 laws, Kirchhoff's first law and the Kirchhoff's second law. The first law is called as Junction Rule or the KCL law, Kirchhoff's current law. This is the diagrammatic representation of the Kirchhoff's first rule or the first law. It is having the 3 connections here. One is having the current I1, I2 and I3. The statement of this Kirchhoff's junction rule is at any junction, the sum of currents entering the junction is always equal to the sum of currents leaving the junction. This is the statement of Kirchhoff's current law. Means when you apply the Kirchhoff's current law to this circuit here, it gives I3 is always equal to I1 plus I2. I3 is equal to I1 plus I2, that is the current entering at A is I3. The current entering at A is I3 here. This is I3. Sorry, this is I3. This will be I2. The current entering through the junction is I3 and the current that is leaving the circuit is through the also equal to I3 here. Means I1 plus I2 means I1 will always be equal to I2, that will always be equal to I3. Junction rule is nothing but the law of conservation of charge. This junction rule is the law of conservation of charge, and the statement for the junction rule is at any junction the sum of the currents entering the junction is always equal to the sum of the currents leaving the junction. Here we are going to consider the sum of currents as I3 is equal to I1 plus I2, where I1 will always be equal to I2 and I2 is also equal to I3. Okay. This is the second law of Kirchhoff. It's called as a loop rule, Kirchhoff's loop rule. It states that the algebraic sum of changes in the potential around any closed loop involving resistors and the cells in the loop is 0. See here in the diagrammatic representation we are having a junction A. At this junction A, the current leaving is I1 and I2 and the current entering is I3. Okay. The junction rule says that, we previously have studied the junction rule, the first rule. Okay. The junction rule states that I3 is equal to I1 plus I2. At a point H, current entering is I1 here. The current entering is I1 at the point H here. There is only one current leaving H, and by the junction rule, that is also the current is I1. Okay. So this is about the Kirchhoff's second rule, and these are the 2 Kirchhoff's rule. The second rule is nothing but the conservation of energy. Okay.